Okay, hi everyone. So today this is going to be the last CaNPAN online lecture. So after that, I will send you via email instructions on how we are going to discuss your research projects, if there will be any the projects you are interested in. Starting from the next week, we will be meeting individually in person with CaNPAN students and discuss the individual mini research projects. Okay, today I'm going to talk about how to use CaNPAN computational tools to model X-ray burst on a neutron star creating hydrogen and helium-rich material. How to model the evolution of this burst using MESA stellar evolution code, followed by post-processing nuclear synthesis simulations with nucleate one-zone code. Okay, I'm going to start sharing my screen now. Okay. Okay, so these are slides that belong to CaNPAN project tools. They are in the repository. You can have a more detailed look at them at home. So I'm going to walk you through the slides. So as I said, the topic today is X-ray bursts and seeing nuclear synthesis, which in this case, in the case of X-ray burst on creating neutron stars, takes the form of the so-called rapid proton capture process, or RP process. Okay, now first, I'm sorry. Yeah, these are just general comments on CaNPAN projects. So I read them last time when I was talking about NOVA evolution and nuclear synthesis simulation. So therefore, I'm going to skip this first slide. Okay, so now let's go to the second slide, which explains what we are going to do today. So in this project, I will focus on, as I said, rapid proton capture process, RP process, nuclear synthesis that occurs during an X-ray burst on an accreting neutron star. So in many instances, this is similar to classical nova explosions, okay? Because again, we have a closed binary system, a neutron star now instead of a white dwarf. A neutron star is now in a closed binary system that accretes hydrogen and helium-rich material from its companion, from the secondary star, which is usually a red giant. Like in the case of nova stars, as the accreted material accumulates now on the neutron star more and more, the early arrived material gets continuously compressed by the new material, by the gravitational force, and ultimately conditions for thermonuclear ignition are reached. The huge energy from unstable nuclear burning at the bottom of the accreted envelope is released in the form of X-rays in a very short time interval. Therefore, this astrophysical phenomenon is called the X-ray burst. So the typical accretion rates for X-ray bursts range from 10 to the minus 11 to 10 to the minus 8 solar masses per year. So which approximately corresponds to mass accretion rates characteristic also for nova events, for nova phenomenon, except that now instead of white dwarf, we have neutron star with much deeper gravitational potential well. Therefore, accreted material gets compressed to higher densities and higher temperatures are reached. In the case of X-ray burst, the peak temperatures can exceed 1 billion Kelvin, 1 gigakelvin, which is suited for rapid proton capture RP process to occur. In nova explosions, if you remember, the peak temperature can reach up to 450 million Kelvin. So yeah, okay. So now here I'm using the slides that were prepared in the year 2015 by Andrew Cumming. Okay, so therefore I give credit to Andrew Cumming. So this is just the first slide. This is just a beautiful picture which shows a closed binary system with a red giant, this a big red star that donates material through the inner Lagrange point to neutron star. And of course, the accretion disk is formed around neutron star, but material eventually, because of the processes that occur in the accretion disk, the material finally ends up on the surface of the neutron star. Okay. Okay. So now let's talk about the low mass X-rays binaries. So this is a case when a neutron star accretes material from a low mass companion. So here in this picture on the left, this is a secondary star, which is a low mass non-degenerate star, normal star, which donates material to the neutron star, this accretion disk, and this is in the middle. This black arrow shows the location of the neutron star. Okay, so orbital periods in these binary systems usually range from 10 minutes up to a few days, depending on the type of the companion star, the secondary star. And as already mentioned, typical mass transfer rates or mass accretion rates are between m dot, between 10 to the 11, minus 11, 10 to the minus 8 solar masses per year. And this is the corresponding values in grams per gram per second. So this mass accretion rates gives an accretion luminosity, m dot multiplied by gravitational constant g, the mass of the neutron star divided by the radius of neutron star. Of course, this gives the change of the gravitational potential energy as a result of accretion, which is responsible for the luminosity during the accretion phase. So, and the characteristic accretion luminosity L sub x is 10 to the 35, 10 to the 38 erg per second. And X means here it's because of the high temperature, this energy is emitted in the form of X rays. And during outbursts, during X-ray bursts, in outbursts, this X-ray bursts sources, they are very bright X-ray sources. Okay. Okay. So now let's go further. So this is schematic structure of a neutron star with accreted hydrogen and helium-rich accreted envelope. So as you know, the typical radius of a neutron star is of order 10 kilometers. So it's shown here, core, inner crust, and outer crust all belong to the neutron star. And here on the right, the radial distances are shown. So the size of the core is of order 10 kilometers, inner crust of order 1 kilometer, outer crust of its depth is of order 100 meters, and so on. But we are going to focus only on this accreted envelope, which will include heavy element ocean, shown with blue, and hydrogen and helium-rich layer shown in green. And you can see the depth of this envelope is only about 100 meters depth, and the density, which is shown on the left, changes between approximately 1 gram per cubic centimeter close to the surface up to approximately 10 to the 9 cubic centimeters, gram per cubic centimeters at the bottom of the accreted envelope. Okay, so we are going to use in this case the mesostellar evolution code, which will model thermodynamic and nuclear synthesis processes occurring only in this envelope, which includes only blue and green parts of the schematic picture as shown here. So this is the structure of an accreting neutron star that is used in MESA. So MESA doesn't, in this case, computes the structure of the entire neutron star from the center to the surface. It only computes the structure, thermodynamic structure, and nuclear synthesis inside this accreted envelope, as I said. So its characteristic depth 100 meters and density from 1 to 10 to the 9 gram per cubic centimeter. Okay, MESA allows to do this to model only part of the star. Okay, so now this figure, these are observational results shown on the left and on the right panels. They show actually light curves from an accreting neutron star. This narrow peaks here, almost this narrow peaks, 1, 2, 3, 4, 5, 6, 7 peaks. These are X-ray bursts. Okay, and between these peaks, the bright curve, the energy, the luminosity comes from accretion. It is just accretion luminosity. Okay, and this green arrow shows that between two X-ray bursts, the luminosity is provided by gravitational energy release. Okay, this energy corresponds approximately to 200 mega electron volt per nucleon. Okay, while during X-ray burst inside each of these peaks, which is shown in the right panel, the luminosity in the peak is provided now by nuclear energy release because of the thermonuclear explosion, thermonuclear runaway, and this nuclear energy release provides only approximately from 1 to 5 mega electron volt per nucleon. So this is less than gravitational energy release between X-ray bursts. So the ratio is shown here. So gravitational energy release between X-ray bursts is approximately 40 to 100 times stronger than nuclear energy release during X-ray burst. But luminosity here is higher because just X-ray burst takes a very short time compared to the time interval between X-ray bursts. Okay. Okay. So this plot is taken, is produced by myself. So using CaNPAN computational tools. So what's shown here are a series of X-ray bursts. This peaks simulated with the MESA stellar evolution code revision 7426. This revision is used in CaNPAN tools to model the evolution of X-ray bursts. Okay, this is done in the MESA run directory with the name XRB for X-ray burst _ MESA _ CaNPAN. I will show you actually how this can be done. And what's shown on this plot, this is luminosity of X-ray bursts measured in units 10 to the 38 arc per second. So we can see it's, as was seen in the previous slides, it's typical luminosities of order 10 to the 38. So therefore, when we normalize it by this value, we get luminosity in these units of order 1 as a function of time in hours. So you can see in this simulation, X-ray bursts occur approximately every 2.5 hours. Okay. So now we have here 1, 2, 3, 4, 5, 6, 7, 8 X-ray bursts, and next plot shows zoomed out 7 X-ray bursts. This one, next plot. Okay. So this is the 7th X-ray burst computed in the series of X-ray bursts with the MESA stellar evolution code. Okay, and you can see it's zoomed out. So now we have here a much shorter time scale. This is time in seconds. So you can see that an individual X-ray bursts actually takes a relatively short time of order 100 seconds, okay, compared to time between X-ray bursts, which that was 2.5 hours approximately, okay. And this plot is made by myself again using this CaNPAN computational tool, X-ray burst measure CaNPAN, and different colored circles along this curve, bright luminosity curve for this individual X-ray burst. Different circles show just different meso models. So you can see when we go from the first model to the last model, this approximately corresponds to 200 time steps, 200 models. So between 3140 and 333. So this is approximately 200 models cover in meso simulations cover the entire X-ray burst. And of course, we can select any of these models and have a look at the internal thermodynamic structure of the neutron star accreted envelope at the corresponding moment of time during this X-ray burst. Okay, so now, so what's shown here is how luminosity changes during one X-ray burst. But of course, remember, so MESA models the entire structure of the accreted envelope. By entire structure, I mean temperature profile, density profiles, mixing diffusion coefficient, convective diffusion coefficient profiles, etc. And therefore, we can extract from this MESA simulation of one X-ray burst, the seventh X-ray burst in this case, we can extract how the peak temperature, the maximum temperature, in this case close to the bottom of the accreted envelope, like in nova stars, how the peak temperature and its corresponding density changes with time during one X-ray burst. This is what in one zone new grid simulations is called trajectory. And ejected trajectory is shown in this plot for temperature, this blue curve. So blue curve shows temperature from this model for the seventh X-ray burst. So you can see as a function of time, again, you see the characteristic time scale here, again, like in the previous plot, 100 seconds. And temperature, the blue curve reaches the peak temperature slightly above 1 billion Kelvin, 1 gigakelvin, okay? And the orange curve shows its corresponding density. While the gray dot dashed curve show temperature from what I call here X-ray burst example, and this corresponding density is plotted with this dotted curve, also from the example. This example lives in new grid example directories, and it can be used in comparison with our MESA model, but the difference is not significant, as you can see. In the example, in the new grid example, peak temperature reaches above approximately 1.1, so it reaches almost 1.4 billion Kelvin, and density is approximately the same. So in one zone nuclear synthesis simulations for X-ray bursts, you can use, and we can use either trajectory ejected from our simulated MESA X-ray burst, which is called here model, or from take temperature, the trajectory, temperature and density as functions of time for new grid X-ray burst example. So two possibilities there. Okay. So next slide just explains the physics. What is called the thin shell, the thin shell flash. Why in the case of, by the way, both nova explosions and X-ray bursts, why this accreted material is actually experiences thermonuclear runaway, thermonuclear explosion. This is because this is a thin shell. So in this case, as the slides explains, in a thin shell, the pressure at the bottom of the shell is actually fixed. So it's determined by the weight of overlying layers, right? So we take the mass of the layer, multiply by the gravitational acceleration divided by the surface of the spherical surface, and as a result, we get that the pressure at the bottom of the accreted envelope is equal to gravitational acceleration g multiplied by the so-called column density, which provides column depth, but it's also called sometimes column density. This is just if we look, if we take a cylinder with a cross area one centimeter squared, 1 square centimeter, and how much material are inside this cylinder in grams. So this is what column depth or column density is. And the pressure is just the product of gravity and column depth. Okay, so column depth is a useful coordinate because it tells us about both mass and pressure. So therefore, it's often used in simulations like this. And this is the pressure scale height, okay, which can also be expressed via the column depth. It's column depth divided by the mass density, okay. Why thin shell experiences thermonuclear explosion flash? This is explained when we consider the entropy equation, which is just well-known thermodynamic law. So in this case, we assume that the pressure doesn't change because pressure is determined by the weight of overlying material, and we are interested in seeing how temperature actually changes during the thermonuclear ignition. Okay, and the change of temperature, of course, the rate of change of temperature is determined by the thermal energy source and sink, and the source is provided by the heating source, which is in this case nuclear reactions during explosion, and the sink energy sink source is provided by cooling in the layer, heat transport to the surface. So cooling, I mean, in electron degenerate material is provided by electron conduction, but it's not sufficient during thermonuclear explosion. Therefore, during thermonuclear explosion, it's replaced with convection. But if heating happens faster than cooling, then we have a situation of thermonuclear explosion. Okay, so therefore, this box emphasizes this fact. When the rate of heating is larger than the rate of cooling, this is when we have a thermonuclear runaway. Okay, and as I already mentioned, so this just summarizes this examples of the situation when the heating rate exceeds the cooling rate. Examples in stellar astrophysics are type 1 X-ray bursts. This is what we are talking about right now. Also classical novae that we discussed last time, and also helium shell flashes in asymptotic giant branch stars, which I mentioned in my first lecture that was about introduction in stellar astrophysics, right? Okay. So now this are again observational data. Okay. So this is helium ignition in a hydrogen-rich environment, because first we have hydrogen-rich, both hydrogen and helium-rich accreted material, right? And therefore, in this situation, when temperature is high, we have actually both hydrogen and helium burning. And this observational data obtained for the X-ray burst source GS 1826-24, they show the events of helium ignition in a hydrogen-rich environment. And so this observational plot, yeah, and on the right-hand side, these are the corresponding numerical simulations of the corresponding X-ray bursts. So here we have mixed hydrogen helium burning, as I already said, But this observational data are provided here because the case which is modeled with Mesa code and this CaNPAN computational tools corresponds. It was tuned up. Parameters were adjusted to reproduce this observational data for this X-ray burst GS 1826-24. Therefore, and as you can see, so this this is what we reproduce also with Mesa code on the right panel here. Finally, this is the last slide of this introduction to X-ray burst physics. It shows a fragment of the chart of nuclides, okay, from neutron hydrogen up to xenon, as you can see. So this field boxes are stable nuclei, so this is the value of stability. And nuclear synthesis that occurs in X-ray bursts is called, it corresponds to the so-called rapid proton capture process, RP process, hydrogen burning in a helium-rich environment. And this process goes away from the value of stability to the left, unlike to S, R, or I process, and unlike to neutron capture process, which takes nuclear synthesis to the right from the value of stability. In this case, we have rapid proton capture process, which follows nuclear synthesis along a path to the left from the value of stability. These are also unstable nuclei, proton-rich nuclei, but at the end of the process, they decay along isobars toward the so-called P elements. And P elements are like this element, for instance, here shown with a field box here. So this is a stable element, but you can see it's shielded from the neutron rich side of the value of stability by this stable nuclei. So therefore, this means that this stable isotope cannot be produced in neutron capture process, because at the end of neutron capture process, unstable nuclei will decay to this stable nuclei, and this one, and this one, and this and this one cannot be reached by neutron capture processes. And there are quite a few of the so-called P elements. P elements are elements can only be produced in rapid P process, and it is these elements that are expected to be produced in nuclear synthesis events such as X-ray bursts, or in some cases co-collapse supernovae. And this nuclear synthesis process can be modeled in one-zone simulations with TINA CaNPAN, with computational CaNPAN computational tools on the AstroHub TINA web server. I will show you this in several minutes. So first we have here, because of high temperature, huge actually temperature, and the presence of high amounts of helium, we have triple alpha reaction. Then we have alpha P process, which release protons, which can be captured by this nuclei and move nuclear synthesis to the left in the region of P nuclei. Okay, so that was the last slide in my introduction. What's about the X-ray process synthesis? Now let's go to computational tools that allow you to do this, to do the modeling of X-ray bursts and the accompanied nuclear synthesis. Okay. So now let me just remind you again that there are three AstroHub gateways here that you can potentially use. Any of CaNPAN students can use TINA and public outreach. And if you are also a NuGrid member, you can also use NuGrid Wendy, right? So it is only on NuGrid Wendy that you can run yourself NuGrid, both NuGrid one-zone and multi-zone codes. On TINA, you can run only one-zone NuGrid codes. And in public outreach, you can run Mesa simulations. Okay, so now I'm going to start with NuGrid Wendy. So assuming you are a NuGrid member, that I am. Okay, so therefore first I go to NuGrid Wendy here. Okay, and let me first show you. So here I'm in my CaNPAN projects directory. So you are supposed to have the same directory, okay? But here I'm on Wendy 2. So as I said, yeah, you can go there if you are a NuGrid member. And in this CaNPAN projects directory, we already discussed Nova. Now we're going to discuss X-ray burst. For this, we can use X-ray burst, okay, RP process directory. So X-ray burst, I go there. Okay, so in this directory, there are 3 subdirectories. So this one contains notebooks with slides that I've just showed you, as well as X-ray burst analysis notebook that I will show you later. This one, Mass X-ray burst Python notebook for analysis of computational data. And there are 2 computational directories, X-ray burst MESA CaNPAN, where you can run MESA evolution computation of X-ray bursts and reproduce those nice X-ray burst peaks that I showed you. And PPN XRB CaNPAN, from its name, you can figure out PPN means one zone nucleosynthesis simulations of X-ray bursts. So this is Wendy too, but one zone simulations can also be done on TINA, even by those of you who are not NuGrid members. I will show you this later how to do so, therefore this is not that important. Now I'm going to focus on MESA simulations of X-ray bursts, right? Also, there is a README X-ray burst file here, and it's open here on my laptop. So it actually explains how you can run MESA stellar evolution code. And remember, MESA stellar evolution code can be run on both Wendy NuGrid, only for NuGrid members, as well as on public and outreach AstroHub Gateway, where all CaNPAN students have an access, and I will show you this later. And this README file just explains how to run MESA simulations of X-ray bursts. So the important thing, there are 2 important things that I'm going to focus in this README file. I'm not going to read it the entire file. You can do this later. But 2 important things are the following. So when you will, if you will decide to run MESA simulations of X-ray bursts, first of all, you can choose between 2 nuclear networks. RP stands for Rapid Proton Capture Process, RP153 or RPNet. These are nuclear networks. So I recommend for you to use RP153, which provides cut off RP process reaction networks. I checked this, although it's cut off, it takes into account all important actually. So the difference with the full network is not that significant. While the larger network, RPNet, it includes more isotopes relevant for RP process, but it leads to much longer execution times for MESA XRB simulations. So therefore, if you have a lot of time, you can let MESA code run for a long time. By long time, I mean maybe a day, 24 hours, even like this. Then you can use this network. But I still recommend you to use this cutoff network, so it runs faster. The second thing, how to make your MESA X-ray burst simulations faster, is this is explained. Yeah, this is explained here. So it says that don't try to run MESA X-ray based simulations with a standard MESA start command, run, which means run, because this command will initiate X-ray based simulations from the beginning, and therefore you will have to wait for a long time. for MESA to calculate a series of X-ray bursts. So I've already done this, and intermediate results are placed in this directory, photos start file. This is a directory, you will find it there. And I recommend here for you to use as a start model, this model, X100, from this file. As is explained here, you will have to copy this model, X100, from this photos start file to your photos, from this photos start file directory to the directory photos, from where MESA takes by default models to start the runs. And then you start the run instead of run command, you start the run with the command RE and provide the name of the starting model X100. So in this case, you will simulate just one X-ray burst, the 7th one, and you can analyze this with this notebook, okay? So now let's go back to AstroHub server here, all right? So now I'm going to this notebook. So the notebook, this notebook is in this directory, of course, okay, in this directory. This is this notebooks, Mass X-ray burst, X-ray burst introduction notebook contains the slides that I already showed you. And now I go to this notebook, okay? Plot and analyze results of MESA-1 X-ray burst simulations, right? So let's execute commands in this notebook. So this cell makes a plot of Hershman-Russell diagram of a neutron star experiencing X-ray bursts. And you can see it's a fragment of the evolution track, but it looks very similar to the corresponding track, to the track for the nova explosion, in the sense that luminosity is increasing during the explosion, in this case from decimal logarithm of luminosity in solar units from about 1 to about 4.5. This is, by the way, the luminosity approximately the same that's reached by nova, and this corresponds to Eddington luminosity. The difference with nova is, as you can see, the surface temperature here is significantly different. Surface temperature here, effective temperature, for novae, it was 10 to the 5, 10 to the 6. Here, the surface temperature can reach 100 million, and therefore we have X-ray radiation instead of ultraviolet and soft X-ray radiation like in novae. Here we have much higher surface temperature. Okay. Now here we select models with all X-ray burst peaks. So where luminosity in units 10 to the 38 solar luminosity exceeds this minimum value, which is parameter here, right? Now we make a plot of all X-ray bursts. Okay. So in this case, as I said, when you run MESA only for one X-ray burst, as I explained you before, it takes about 2 hours instead of 24 hours to run MESA simulation just for one X-ray burst. The long time is taken because we have a lot of isotopes taking part in nuclear synthesis. This is the main reason, okay, in this case. So therefore, MESA is relatively slow here. Okay, so therefore here, my MESA calculations, simulations followed just one X-ray burst. So, and this is its plot, X-ray burst, in this case, number 1, it says. Okay. But because there was just one X-ray burst in this case, but this is the 7th, actually, okay. So now we here I plot X-ray burst luminosity as a function of time in hours. So time in hours, you can see we have a nice peak. Luminosity in the same units, 10 to the 38 solar erg per second. Now, plot X-ray burst luminosity is a function of model number, which is of course different from time. and this is a function of model number. Remember, I told you here model number starts from 300 to 140 approximately and goes to 303 and 3 something like so. It takes approximately 200 models. Takes about 2 hours to calculate 200 models just to follow one X-ray burst peak. Okay, so now we read results. Plot selected X-ray burst. This is the same, the 7th one. So you can see this is the same plot that was included in the slides that I showed you. Okay. So now plot mass accreted by neutron star. So you can see this is as a function of time, the accreted mass. So the accreted mass is very small because the accretion rate is here very small. And the time interval is also small, but this accreted mass, although it's small, but it's enough to trigger thermonuclear runaway. Now, next cell plots radial temperature profiles inside the accreted envelope for the selected X-ray burst. In this case, the 7th one. So this will be temperature profiles. Yeah, you can see. So a decimal logarithm of temperature in Kelvin as a function of radius. This is inside only of accreted envelope. So you can see radius here changes from 0 to approximately 5,000 centimeters, which corresponds to 50 meters. So remember the depth of the accreted envelope of order of 100 meters, okay? And the peak temperature, as you can see here, reaches 10 to the 9, slightly above 1 billion Kelvin. And different colors, different curves show different models, MESA models, okay, shown here. So temperature, of course, as time goes on, temperature increases. And the envelope, as you can see, as a result of thermonuclear explosion, envelope expands, similar to what we had during nova explosion as well. Now let's plot the corresponding density profiles. These are corresponding density profiles. You can see here the peak density, that's not Kelvin, this is gram per second, can reach at the bottom up to almost 10 to the 7. Okay, and now let's plot radial profiles of elemental abundances. These are selected elements here: hydrogen, helium, carbon, oxygen, and iron. Okay, and these are their profiles. So you can see when we approach the bottom of the accreted envelope, we have production of iron here. Okay, we have production of carbon, oxygen, and iron. While in the outer part of the envelope, we have just hydrogen, helium, and yeah, the small amount of iron corresponding to solar chemical composition. This is what's accreted from a companion star. Okay. Now, the next cell plots diffusion coefficient profiles. Okay, now. Now, the notebook makes a plot of trajectories. So this is the same plot that was shown in the slides, so I'm not going to discuss it anymore. And finally, here we can extract, we have just extracted trajectory from our MESA simulation of one X-ray burst, and now we can save this trajectory in a file and use it in one zone PPN grid nuclear synthesis simulation. So now the last cell saves trajectory file. Okay. So now we can go to directory PPN X-ray burst. This one. Okay, and run here one zone new grid simulations with the trajectory that we've just extracted from MESA simulations. But instead of this, now I'm going to switch from NuGrid Vendi server to TINA server, because TINA server allows everyone, all CaNPAN students, to do the same one zone nucleosynthesis simulations for X-ray bursts. So now I go to TINA, okay, and like in other projects with TINA, so here we have standard notebooks, Model Runner notebook and Result Explorer notebook. Okay, so I'm not going to repeat to explain them. So in this case, Model Runner notebook runs simulations of one-zone simulations of nucleosynthesis in X-ray bursts, and this text here explains that for this one-zone simulations of X-ray burst nucleosynthesis, you can use here one of two trajectories. Either the trajectory that was just extracted from our MESA simulations, trajectory input X-ray burst MESA, or trajectory input X-ray burst example from NuGrid example, which has a higher temperature. So here, before today's lecture, I did this run. It takes a relatively long time, maybe 15-20 minutes, because here I wanted to include also the output of reaction rate fluxes. And usually when you include, I explained this before, how to include reaction rate fluxes, this takes a longer time, even one-zone simulation, so therefore I have already run this, okay? And here I have chosen, as for trajectory of X-ray burst, this example trajectory with a higher temperature, which reaches 1.4 billion Kelvin. And then, as usually, I saved the results in a file with name X-ray burst example. And now I go to Result Explorer notebook, which analyzes the results that were obtained with Model Runner. Okay. So you can see here, I use this X-ray burst example directory where I saved results when I run one-zone simulations with Model Runner notebook. Here, this is the name. So this cell just reads output data. Okay. So now here we make a plot of elemental abundance chart. Okay. Takes some time, yeah, like this. So there were 1,999 time steps in one-zone calculations, and here I make a plot for the final time step at the end of integration. So we can see indeed here we have production of proton-rich unstable nuclei. So we have actually here rapid P process. So this solid boxes show the value of stability, and you can see the nucleosynthesis goes along a path in the to the left from the value of stability in the region of high proton numbers here. Okay, the color shows decimal logarithm of mass fraction. So red corresponds to mass fraction close to 1, and you can see, yeah, these are unstable isotopes, and of course at the end of nucleosynthesis they will all decay along isobars diagonally like this toward the first stable isotope. And for instance, these are typical P elements, this one, this one, this one, this one, this one, okay? Yeah, so I'll go to the next cell. So here we just make a plot of the trajectory that was used. So you can see this is a trajectory for X-ray burst model XRB example, which has maximum peak temperature above 1 gigakelvin, not like from our MESA model, but it's taken from NuGrid example. It has higher temperature that will reach almost 1.4 billion Kelvin. And this is its corresponding density as a function of time. So now here we make a plot of reaction rate fluxes because I asked one zone code to output fluxes, which takes a longer time and requires big files. And you can see here again, these arrows show the strengths of the corresponding nuclear reactions. So the strengths are shown with the thickness of there and with its color. So the yellower the color, the stronger the corresponding reaction flux. For instance, we have yellow color here, here, and here, which means this particular and you can see these are proton capture reactions because they go upwards, and upwards corresponds to increase of proton number. So these are proton capture reactions. Diagonal lines correspond to decays, beta decays, etc. So here you can see how actually nuclear synthesis, this rapid nuclear synthesis, proceeds on the chart of nucleides. Okay. So now here we plot decays, elemental abundances. So these are decayed elemental abundances for X-ray burst model, X-ray burst example, cycle, time step, integration time step, the last one in this case. So you can see decimal logarithm of mass fraction of a stable element with respect to its solar abundance. And you can see for intermediate mass elements here, we have a huge production. So our production compared to solar, 6 orders of magnitude in this region: molybdenum, ruthenium, rhodium, palladium, niobium, zirconium, etc. Okay? You can do this analysis yourself if you're interested in. Okay, so now let's move to this plot. Let's plot isotopic about composition for a second. Reason dictate. Okay, let's plot isotopic composition for the X-ray burst. Yeah, this is isotopic composition. These are undecayed isotopic abundances for the same model. Okay. Yeah. So this is TINA. So you can do this. You can study this with slides, with README files that explain what you can do and what's actually happening here. Okay. And I think that's it. So I explained to you how to run a MESA on Venn nucleate for nucleate members, and how to run one-zone simulations also on nucleate Venn, or alternatively on TINA. So I recommend for those of you who don't have access to nucleate Venn to use TINA X-ray burst if you're interested. Now at the end, I'm going to show you actually how to use how to run MESA and do some analysis of nucleosynthesis data on AstroHub server, public and outreach, which is accessible for all CaNPAN students as well. Okay, so now let me go to public outreach. I already opened it here. So when you enter public and outreach server, you will see here on the left in the file manager 2 notebooks. The first notebook is called Install, Run, and Analyze, and the second notebook is called Star Explore, right? Yeah. So let me first explain you what you can do with these 2 notebooks. Install, Run, Analyze. It's open here. Okay. I'm going to close my file manager. So install, Run, Analyze MESA notebook allows you to, first of all, to install here any MESA revision, not necessarily MESA revisions 53, 26 or 76, 24 that CaNPAN tools use for corresponding in NOVA and X-ray burst MESA simulations. But here you can play with other MESA revisions. Okay, I'm not going to explain this in detail because you just can read all this text and comments. It's pretty straightforward. Okay, For instance, you can install Mesa revision 10.398 or the most recent one and try to run it. So here you will be able to run this, to make the code and to run the code, okay? Please pay attention to this comment, which is shown here with bold font. At this point, please change the kernel to Python 3 and continue for analysis and plotting of data. This should be done because before this cell, as you can see, the notebook executed Linux commands. So therefore, before this, it uses, as you can see here on top right, it uses bash mode. Bash mode means execute scripts, Linux script, shell scripts, okay, operational system shell scripts. But after this cell, you are going to execute Python commands in this notebook. So therefore, after this cell, after cell run, please change here bash. You go to kernel and change kernel. Here you select Python 3, right? Okay, so please don't forget to do this. So please pay attention to this recommendation here. And then you can make some simple NuGrid Py plots to analyze the computations you did in this cell previously, okay? So by NuGrid Py plots here, I mean details actually details are provided here in NuGrid Py documentation. So you should just read this and try to use them. So I'm not going to repeat this again. Okay, so this is one notebook. This is the notebook install, run, analyze, which is available, as I said, on public and outreach server for any CaNPAN student, okay? So now let's go to the second notebook, Star Explorer notebook. It's open here, okay? So the second notebook here allows you to analyze already available results. And these results actually, there are different results. They are taken from a database of NuGrid Stellar models, okay? So these are actually models that were published in NuGrid papers, NuGrid Stellar Dataset 1. This is year 2016, and as well as NuGrid Stellar Dataset 2. This is what we call NuGrid models. There were, as you can see, a lot of models with initial masses from 1 solar mass to 25 solar mass, with different initial metallicities from 10 to the minus 4 to solar, nearly solar metallicity. And these models are all been kept on a server. And with this notebook, you can have an access to this data to analyze them, to make some plots. And let me show you how to do this. You can try to run this notebook. So it's also almost self-explanatory. Therefore, I'm not going to explain for you every cell. Just read the comments and text. So you can see the first cell executes the following 3 cells to make a keep-in-hand diagram of the 25 solar mass star template case, like figure 2 in this paper, okay? So when you execute this, let me check this one, you will get a keep-in-hand diagram of the 25 solar mass star during its entire evolution from the 0H main sequence up to the almost iron core collapse. Okay, it takes it takes some time, but less than 1 minute. So you can see this is a keep-in-hand diagram of a 25 solar mass star. So this is enclosed mass in solar units. So 0 center, 10. This is 25 solar mass star. So therefore the surface is here upstairs somewhere. So as a function of time. So of course, yeah, usually time, if you are interested in following the evolution almost to the iron core collapse, therefore time is usually plotted in these units. So this is actual time minus the final time, t end, decimal logarithm, and time is in years. So this transformation of time is required so that all evolutionary phases occupied approximately the same space on this CaNPAN diagram. As you can see, we start, this is just hydrogen convective core. Its mass decreases on the main sequence. This is the helium convective core. Then we have shells here, helium shell burning, we have then carbon shell burning, oxygen shell burning, and so on. Okay, let's continue. So please have a look at this notebook, try it, read all the text. I'm not going to explain details. Okay, so now analyze new grid data. And here by new grid data, I mean those data from those publications that I just showed you. Okay, so here you can choose the model from those data. You just specify the mass, 2 solar masses, and metallicity. This is the solar metallicity approximately. Then this cell will find this model, as you can see, in this database. Okay, new grid data. And then you can make different various plots for this model. Okay, for instance, here, this is CaNPAN diagram of this model. So this model was assigned to this instance S, and then we, for this instance S, make different plots. CaNPAN, this is not just CaNPAN like I showed you before. This is CaNPAN carbon oxygen. So it shows carbon oxygen ratio as a function of model number. Because this is two solar mass model, and it goes through the asymptotic giant branch phase, which is actually shown here. So you can see these small features here are helium shell flashes, and following each helium shell flash, there is third dredge up, which brings fresh carbon to the surface, and as a result, this black curve shows, you can see as carbon to oxygen surface ratio increases with time, in this case with model number. So, and when it exceeds the ratio carbon to oxygen 1, the star becomes carbon star because carbon dominates in its atmosphere. Before this, it was just oxygen star, the normal, the typical, the ordinary red giant. Above this, it becomes carbon star. Okay, and now this plot shows this cell makes a plot of central temperature versus central density in the same model. What's at the surface? So this is just Hertzsprung-Russell diagram of this model. So it starts on the pre-main sequence phase. Here, this is pre-main sequence approach. Okay, this is zero-H main sequence. This is main sequence. This is subgiant branch. This is red giant branch. And this loops corresponds to helium shell flashes on the asymptotic giant branch. Okay. So this is again another form of the CaNPAN diagram for the same model. So this dashed gray region is convective envelope. The total mass is 2 solar mass. As you can see, the total mass decreases with time because of the mass loss. Okay. And this convective envelope, and this are gray shaded regions are convective helium shells during the helium shell pulses, as you can see. So there are quite a few pulses here, 1, 2, 3, 4, etc. About 20 helium shell pulses. Okay, so this cell makes a plot of carbon abundance as a function of mass coordinates. So inside the model, here we have selected for this model the same mass to the same metallicity. We have selected the model number 4500. We can see 4500 is approximately here, while this model already has a carbon oxygen core. Oh. not yet, no. It's still helium core because carbon abundance here is too low here. Okay, now the next cell, by the way, this notebook is also useful because it teaches you how to use basic grid pi commands and how to get to extract useful information. For instance, it shows, this cell shows available columns in the data files, okay? What in principle you can plot quite a lot of different things you can plot. This shows how to extract just temperature array from the model. So it gives array of temperature, decimal logarithm temperature, starting from the surface where temperature is 3.6 approximately 4,000 Kelvin, and this is the temperature of the center, approximately 100 million Kelvin. And then this cell shows header attributes in the file. Okay, now so the previous cells, they allowed you to make analysis of MESA computations of this model, MESA computations, so stellar evolution computations of this model. Now, starting from this cell, as the title here explains, you switch to the analysis of new grid multi-zone post-processing data for the same model, but you can, of course, to change the model. And all these models, as I said, they are taken from new grid sets from those papers, if you're interested. And here we do analysis of multi-zone new grid post-processing. Again, we make an instance of this for the same model, but now it's new grid data. Again, we check what's in header attributes of these models, what's in the columns, okay, of these models, mass, radius, density, temperature, isomass fractions. This is mass fractions of different isotopes. And now we can make plots. For instance, we make plot of temperature as a function of mass, okay? And this is for the model with number 1000, so this is close to main sequence. Therefore, the central temperature is slightly above 20 million. This is main sequence. Now here we make the plot of abundance profiles here for the same model. As you can see, nice abundance profiles as a function of mass. Okay, and this is now for the model number 18,000, which means it's already on the asymptotic giant branch evolutionary phase, right? Therefore, we have here carbon oxygen. So this is helium shell, actually. You can see this is not an entire mass range. This is helium for the helium shell. So helium 4 abundance here, this helium shell, this is hydrogen, etc. Okay, and now we can also make a plot for the formation of the carbon-13 pocket after the helium, between the helium shell flashes and carbon-13 pocket. Formation of the carbon-13 pocket, as you know, is required for the US process on low mass stars. Okay, so, and this is the results of US process in the formed carbon-13 pocket. Here you can see there is barium formed here in this pocket, barium abundance, some lead abundance. You can do this analysis, play with this, so I'm not going to discuss this in detail. There are quite a lot of comments. It's relatively straightforward. Now let me show you how you can use this server, public and outreach, to run MESA simulations for NOVA from NOVA framework, as well as for X-ray burst. Okay, so this is via, as you can see, an outreach server, and here we can go to the directory user Scratch outreach. Okay, and this is this directory /user/Scratch 14_outreach. This is where you can make, you are allowed to do this. You can make your own directory with your name. For instance, you can see, excuse me, there is directory here with my name, Pavel, right? And I go there, Pavel, right? And here, as you can see, you can clone here repositories. You can clone here CaNPAN project repositories, right? You can do this. So now let's go to my CaNPAN project repositories, right here. And now we can go to Nova, for instance, Nova, right? Nova. We can go now to Nova framework because this is where we run Mesa Nova simulations, right? And I go to Neon Nova, the examples I showed you last time, okay, on the vending grid server, okay. And this is a directory where you can actually run Nova simulations, okay. So for this, of course, you have to execute the pair of commands so that you pick up the right revision of Mesa, okay, for outreach. And this is the same, actually, I can show you. Okay, so this is the same thing, actually. This is the same thing that is recommended to be done on Vendy, Grid Vendy. These two commands, export Mesa dir Mesa 5329 and export this one. So you actually should execute these two commands here and this command. Okay, then you make clean, okay, and then you make mk make, and it should not report any errors. Yeah, no errors. And now you can run here Nova Mesa Nova evolution computations, as I explained last time. So therefore, I'm not going to explain this again, right? So this is actually, again, this is where you are when you just entered public outreach. So you go to user, scratch outreach, and here you find your directory, like this one. So I have two directories, so therefore I should go to Pavel Den. It's my other directory, CaNPAN projects. You can make your own directory with your own name and clone the CaNPAN project, okay? And here, if I go to Nova, Nova framework, Neon Nova, and you can see here, I already have results, the same results that I showed you last time. These are results, but these results were obtained not on the server Vendy, NuGrid Vendy, to which there is access only for NuGrid members, but here on public outreach that can be accessed by any CaNPAN student. So here you can do the same Mesa stellar evolution runs that can be done on NuGrid Vendy. Okay. Similarly, here you can, instead of Nova, go to X-ray burst RP process, right here, and then you go to XRB Mesa CaNPAN, and this is where you can run Mesa evolution simulations of X-ray burst, as I explained to you today. Okay, so you can do this. So you can again use public outreach to run Mesa simulations of Nova and X-ray bursts. Okay, you can use Tina to run only one-zone simulations for different types of nuclear synthesis. And if you are a NuGrid member, you can do all runs on NuGrid Vendy. Okay, that's it. I think that I was going to tell you about today. And now that was the last CaNPAN online lecture. Starting from next week, I will send you an email where I will explain you how we can organize our individual online meetings, where we will discuss with you individually. I will discuss with each of you who is still interested possible mini research projects that you will be doing till the end of this academic year with my help. I will be ready to help you, to supervise you. Okay, I have a chat here, just a second. Okay. So that's it for today. Do you have any questions? Yeah, you're welcome, Stephanie. Yeah, so this is the last lecture, and as I said, okay, I will send in email. Actually, in my email, I still have 10 minutes. I can tell you, in my email, I will ask you, each of you who is still interested, of course. I will ask each of you to briefly describe what kind of projects you are interested. Okay, so given that now you are familiar with basic CaNPAN computational tools that can be used, I didn't presented that, but I mentioned that before, that in principle there are more CaNPAN computational tools. Let me I mention them right now. So there is also CaNPAN computational tools that allows to do multi-zone calculations of nuclear synthesis occurring in a neutron star accretion disk, okay, which is called SENSI. The package is called SENSI. Also, there is a big package that allows to do Monte Carlo simulations related to the impact and uncertainty and sensitivity study of nuclear reaction rates relevant for a given type of nuclear synthesis. But these are big projects which require actually a new grid membership. So therefore, we can discuss how to use this project individually, because this will take much longer time than 1.5 hours available for an online lecture. So, but if you are interested in projects like this, Monte Carlo simulations or nuclear synthesis in a neutron star accretion disk, this is also possible. With my help, I will individually explain you how to do this. Okay. Okay, I think that's it. Otherwise, so I'm going to stop recording.